Okay, so let me welcome you to my talk. It's about detecting hardware keyloggers in software. Let me start with a short introduction of myself. My name is Fabian Mihailowitsch. I worked as a former software developer for a German energy combine and am now working as IT security consultant for a German company called DeepSec GmbH, doing penetration tests, source code reviews, and my contact details you can find on the bottom of the slide if you want to contact me after the presentation. So today we are going to talk about hardware-based keyloggers, basically PS2 and USB-based keyloggers. And in general, people think hardware keyloggers cannot be detected in software. And for example, you have that nice quote on Wikipedia, which is like, visual inspection is the primary means of detecting hardware keyloggers since there are no known methods of detecting them through software. However, today I'm going to show you how to actually detect them in software. Why have I done the whole stuff? Basically, because if you Google and try to find information about how you can detect them, you will find less information. There's been done less research on the whole topic, and you won't find any practical ways that actually can be used to detect them. So, but they are a threat. You have this famous case in the year of 2005, which was in Great Britain with the Sumitomo Bank, where attackers paid the cleaning staff to install hardware keyloggers in the banking in order to get passwords and try to steal 423 million US dollars. And maybe some of you guys also had incidents in their company with hardware keyloggers. I've heard of 2 companies. Yeah, so it is a threat. Furthermore, you can't go to every client in the company, try to detect hardware keyloggers by physical inspection. If you have multiple hundreds of clients, you just need to have a software which you can roll out and try to detect it in software. So that was basically the why. Let's start with a short introduction of hardware keyloggers. Basically, they are available for USB and PS2, like I mentioned. They are available as keyboard module, which you can solder. It's basically a chip which you can solder into your keyboard, or you can buy it completely and just plug it in. They are available as mini and PCI cards, which try to get keystrokes via DMA and stuff. But basically, we will focus on USB and PS2-based ones. They are placed between the keyboard and the computer and record every keystroke that's typed on the keyboard. Later on, they have to be retrieved, of course. And there are different possibilities, like some models provide software which reads out the memory of the keylogger. For most of the models, you actually type in the password on the keyboard, and the keylogger then acts as a ghost keyboard and starts to send the recorded keystrokes back to the client. Some models have Wi-Fi access and send emails, others send the keystrokes via Bluetooth, so there are plenty of possibilities. And features of current keyloggers they are up to 2 gigabytes of flash memory, so you can log basically plenty of data. They provide encryption, so the keylogger gets lost. Nobody can recover the memory unless he has the right password. They have timestamping functions where every keypress is assigned a timestamp, and you can create time use charts to see when was the computer used. They have search functions to search through the logs. You have models where you can upgrade the firmware, so it's quite complex. Those devices have plenty of functionalities, but they are quite cheap. They start with a pricing of 32 US dollars for PS2 and like 58 US dollars for USB, so yeah, quite cheap. Another interesting thing, I guess, is who is on the market, which companies are there. Actually, you just have 2 big companies. They are Keycarbon from the US and Keydemon, which has various names. It is also known as Keylog, which is from Poland. And those 2 companies basically have most models which can be bought. And the key daemon models are quite often rebranded. For example, if you look at models like Keycobra and Keylama, in most of the cases, it's just a rebranded key daemon product. Then you have older, but also famous keyloggers which are out there in the wild, like Keycatcher, you have Keyghost, Keyshark, and then you have some other keyloggers, like exotic keyloggers from China. You have like 2 or 3 open source keyloggers, which you can find on the internet and put together yourself. Yeah, so that's basically the market. Before I start to detect keyloggers, I would like to give you a short introduction of how PS2 works and how USB works. Let's start with PS2. If you think PS2, okay, it's not that interesting since currently most people use USB. Okay, yeah, but it's still in the wild. And for example, on that computer, it's a 2-month-old ThinkPad. The internal keyboard actually is connected as PS2 keyboard. So it is still there, and I think it makes sense to have a look at it too. So for PS2, you basically have a keyboard, which is a wire matrix, and once you press a key, the circuit is closed. The microcontroller, which is inside the keyboard, registers the keypress and sends the specific scan code to the keyboard, to the computer. Once you press the key, it sends a make code. Once you release the key, it sends a break code, which basically is the same like the make code, but just the first bit is switched. On the PC hand side, you have a keyboard controller that actually receives all the keystrokes and stuff and can be accessed via the port 60 in order to retrieve the data, and port 64, which basically is a status port. The obvious communication, of course, is the keyboard sends scan codes to the KBC, sure. Not that obvious, actually, is there are plenty of other communication channels. For example, the computer via the KBC can set the repeat rate of the keyboard. It can tell the keyboard to do a reset or perform a self-test. It can basically ping the keyboard, which you can see here. You send EE to the keyboard, and it responds with EE. It's basically like a ping, and yeah, plenty of other functions. The PS2 interface, I'll just go quick over it. I guess most of you know the port, have seen that one. Interesting are basically just 2 pins, the data pin and the clock pin, which are used to transfer the data. And the clock is defined by the keyboard, which can be between 30 and 50 nanoseconds. The data that are actually transferred via PS2 are transferred in 11-bit data frames from the keyboard side to the PC. You have like a start bit followed with 8-bit of data, which actually are the byte that's transferred, which is seen. Then you have a parity bit and a stop bit. And for the KBC side, you have basically the same, but with an additional acknowledge bit sent by the keyboard. Here you can see how it looks like on the wire. Basically, you have the clock, and you basically have the data which are transferred right here. So it's quite simple for PS2. Okay, the first thing when I tried to detect them I came up with is current measurement. You plug in additional hardware, so you have additional electronic components which consume power, and you basically can measure it. If you go on the line physically, you can measure key daemon consumes like 65 milliamperes and Keycatcher 54. So you can detect that more current is drawn, but sadly you cannot measure it in software since the motherboard just doesn't provide any sensors or stuff to actually measure it. So the next idea I came up with is, like I said, keyloggers are password protected. And typically you plug them in, you type the password on your keyboard, they unlock, act as ghost keyboard, and send fake keystrokes, or the recorded keystrokes. And the nice thing about that fact is most keyloggers are shipped with default passwords, which probably won't be changed. Some vendors even recommend not to change them, because the problem is, once you forget the password, you can't simply reset it. You have to send the hardware back to the vendor, and he will reset it for you. So there's quite a good chance people won't change the default password. So my idea was to perform a brute force attack of that password in software and check on the PC hand side whether I can recognize ghost typing. Problem I came up here is the tested hardware keyloggers I had didn't tap the data line passively. Instead, they were placed inside the line. I tried to visualize it in that picture. You can see the keyboard and the PC, which have the data and the clock line, and the hardware keylogger, which is placed in line, really is placed in line. It doesn't intercept it passively anyway, but it's in line. So the hardware keylogger actually knows how the data flows. It can recognize whether the keystrokes are sent from the PC hand side or the keyboard side, and so you can't simply inject fake keystrokes via the KBC. But the cool thing about that stuff is, during my tests, I found out that certain keyboard commands you send to the keyboard actually lead to fake key presses, which probably is because of the response of the keyboard is interpreted as key press. So you can send certain keyboard commands from the KBC to the keyboard, and you can provoke fake keystrokes, which are recorded by the keylogger. So what you can do now is you can create a translation table, which keyboard command leads to which key press, and then you can try to perform a brute force attack via software, and it does work. The problem about the practical use of that is you only have a limited amount of jars. You just have like 10 jars, and so that way you can't brute force all passwords, and it just works for some models. However, since it does look quite nice at least, I want to show you a short demo. What I'm going to show you is, basically I wrote a small program that tries to brute force the password, and afterwards it just opens Nano, and if the keylogger would be unlocked, it would send its fake keystrokes to Nano. So if we have no keylogger present, we won't see anything. Here you can see no keylogger present. Quite blurry. We start the brute force program, Nano, nothing happens, sure, why should it? So if the keylogger is present instead, you can see it's the black box here, if it is present. And now we start the brute force program and Nano. You can see it actually was unlocked right now and send its fake keystrokes to Nano. So just quite nice to show, although it's not that practical. Okay, the next idea I had was maybe there are changes on the data line. Since the hardware keylogger is actually placed in line, it might change the signaling on the line, which would result in a different data set, which is seen or retrieved on the KBC side. Maybe there's an own clock since it gets the data and it passes it on, and the clock is defined by the keyboard and can be between 30 and 50 nanoseconds. Maybe it just does his own transmission with another clock. Maybe the data and the clock signal is dislocated in some way, or any other stuff you actually can see. So what I did is I took a logic analyzer and I tried to tap the signals directly at the keyboard. So once the keyboard sends the signal, I get them. And I tried to tap the signal after the keylogger, so I can see how the data looks when the keyboard sends it and how it actually looks like after it has passed the keylogger. And you get a nice graphic like this. You can see the keylogger, which is basically the clock and the data. You can see the keyboard, data, clock, and you can't see anything. But if you take a closer look at it and try to zoom in, analyze it in more detail, you can see when the clock in that example is pulled low, you can see the keyboard pulls the clock to low, and the keylogger does the same, but with a slight delay right here. Once it is pulled back to high, the clock, in that sample, it is at the same timing. So what we can see out of this actually is the clock cycles are shorter once the keylogger is present. Which, like I mentioned, is probably because the hardware keylogger just sends the data again and just does his own clock signal and stuff. and you can detect it on the wire. I just have showed you it. Problem is, you can't detect it via software. The keyboard controller that is actually used has the possibility to check the clock state, but it isn't accurate enough during a transfer. You can't ask that accurate how the current clock state is to determine that clock cycles are shorter. So you can't, again, do that measurement in software. But another cool thing we actually saw is the clock signal started later when the clock was pulled low. And like you already can imagine, it is basically if you say, I want to detect hardware keyloggers, every guy says at first, hey, you try to do it with timing. And so we saw there's a delay, and yeah, maybe try that timing approach. So since the hardware keyloggers, like I said, are placed in line, the microprocessor has to get the signal. He has to process the signal, write it to his memory. He has to write it back, send it to the client. And this additional logic that actually is introduced increases the signal propagation time. In that example, I have a data transfer. Basically, it starts, and yeah, you can see there's the dislocation we had in the previous graph too. But once the whole transfer is ended, you can see right here, there's a small delay. You have the keyboard once it stops sending, and the keylogger once it stops sending, and you have the small delay. So what you actually can try to do now is to perform time measurement in order to determine whether additional hardware, aka the hardware keylogger, is placed in line between the keyboard and the KBC. So the idea I had is we have various keyboard commands, like I mentioned earlier, which we can use as kind of a ping, like from TCP/IP networks. So I just wrote the small assembler code which sends the identify keyboard command, which actually is F2 via port 60, which is the output port of the KBC, and that kind of stuff just is checking whether we can write. And then I go into a loop and wait until I get the response of the keyboard for MF2, which actually is FA. The whole stuff here I'm doing in a loop like 10,000 times, and so I basically send a command, wait for the response, send a command, wait for a response, and do it various times. So I can measure how much time it takes if a keylogger is present and if no keylogger is present. Problem about that, many problems, is that actually the delay introduced by the hardware keylogger is very, very small. That means running the code from user land won't work at all. Running the code from kernel land or stuff won't work either, because you have like scheduler, you have interrupts, and you don't get an exact measurement. It just doesn't work. That means you have to run your code completely exclusive to get the most accurate measurement you can get out of it. So what I did is I wrote a small loadable kernel module for Linux and tried to get the CPU exclusively. Therefore, I disabled kernel preemption, I disabled interrupts for the processor, I got the big kernel lock, and all kinds of stuff just to get the CPU exclusively and then run my assembler checking code I showed you on the previous slide. Once the code is running, I need to measure the time it takes to run, actually. And since we disabled interrupts, we don't get accurate timing and stuff anymore. So what I basically did is I just read out the processor's timestamp counter, which is the RDTC register, which is increased every clock cycle, and we just can count the number of clock cycles it takes to run our code. If we want to, we can calculate based on our CPU and the number of clock cycles back again the time it takes to run the code, but we don't need it either. We can just work with the clock cycles anyway. It can't get more accurate, so yeah, just use that one. Afterwards, after my measurement, I write the result to the kernel message buffer so I can retrieve it from user land and just restore everything, and we are fine. And that's actually the results. You can see in the setup, the keyboard, 3 PS2-based keyloggers I used, KeyGhost, KeyCatcher Mini, KeyCatcher Magnum, and the number of clock cycles it actually took to run the code on my CPU. And what you can see right now is that for the keyboard, it takes 3381, and once these are present, you can see this increased to 3385, 3386, and it actually takes more clock cycles to run the code, and it's reproducible. I mean, it's not just one test I've done. I've done various tests, and it works reliable on my system. So we actually can detect PS2-based hardware keyloggers, which are based inline, using a time measurement with the code I wrote. At first, we basically would do a measurement without a hardware keylogger. Then we would define a baseline. In that example, we could use 3382 as baseline. Then we can run the code again, like checks for an AV software. And once it is above the value, we can say, okay, some stuff was plugged in line here, and detected. Once it is detected, we maybe even would like to defeat the keyloggers. So the idea when defeating the keylogger, my first idea was just fill the keylogger memory. As I said, the keylogger locks all stuff to the memory, so if you fill up the memory, something will happen. And what actually happens depends on the model. Some models just stop logging once the memory is full. Other models start to override the memory at the beginning. And anyway, it doesn't work anymore. It overrides the keystrokes, or it doesn't log at all. So And as I said, during the brute forcing I showed you in the video, we had keyboard commands that are interpreted as keystrokes. So what we can do is we can use those commands and not brute force the password, but just inject keystrokes, which the keylogger, once he does not recognize the password, will just write to his memory. And I did so and tried out, and I managed to write 100 locked keys in 10 seconds, which means like 10 keys per second. If you take the PS2 models that are on the market, like the ones I had like 64 kbytes of memory, and if you calculate how much time it needs, you come to 109 minutes it takes to fill the complete memory. So I thought, okay, that's too long, you have to find another solution, and I tried to look at the keyboard command. There's a command which is called EE, the resend command, which actually the KBC can tell the keyboard to respond with the last sent byte. But that didn't work either. It took even longer. I just managed to write 4 keys in 10 seconds. So didn't work. So the question, is it practical? No, it isn't. I mean, it works, and the cool thing is most PS2-based models, since they aren't developed anymore that hard like the USB-based ones, they don't have up to like 2 gigabytes of memory. Most PS2-based models have a few kbytes, so you can fill them within 1 hour, it works. But who wants to wait 1 hour before he actually starts to use his computer? And that's the reason why it's just not practical. But it would be even cooler if we could stop the keylogger from reading our keystrokes instead of just overwriting its memory. And we can do that too. Like I said, once you press a key on your keyboard, the keyboard generates a scan code which is sent to the PC. And you have a make code, break codes, and all those scan codes are defined in a so-called scan code set. The cool thing about that, again, is the scan code set can be set by the KBC. And you have that command F0 to set the scan code, and you have 3 scan code sets which are available, basically 1, 2, 3. We normally use scan code set 2. And the cool thing about that is all the hardware keyloggers I had just understood scan code set 2 and 3. So if you switch to scan code set 1, the hardware keylogger doesn't see what's going on and doesn't log any stuff, actually. So it is blind. It doesn't see what's happening. And so the idea just is tell the KBC to say the keyboard, choose scan code set 1, and we are fine. However, since our operating system doesn't see anything either, we have to define a new mapping of the scan code to the key code set. But for Linux, we can do this with tools like hdef, HAL, set key code, so it's no problem at all. Okay, that's it for PS2. Now let's see what's with USB-based keyloggers. Like for PS2, I would start with maybe annoying, but I think it's necessary, introduction of how USB actually works in order to see how we can detect USB keyloggers. For USB, you have like a host controller, you have hubs which are plugged to that host controller. Down to the hubs, you have certain devices, and so you create a tree structure. Each device has various endpoints in return. An endpoint basically is just like a buffer. You can imagine you have an input buffer or an output buffer, and that's basically just what an endpoint is. And each device has an endpoint 0, which is used to set and to get the device configuration and just configure it. Interesting for us are especially low-speed devices, since keyboards, USB keyboards are normally USB low-speed devices, and there you have the endpoint 0 to configure it, and you have like 2 endpoints with 8 bytes. Another interesting thing is only the host controller manages the communication with the device. The device doesn't send any data. The host controller polls the data. Now you might say, okay, for a keyboard, but once I press a key, it must be recognized by the operating system right now. That's done in the device configuration. Once the keyboard is plugged in and changes its device configuration, it has to define how often it wants to be polled, so no keystrokes are missed. And the data transferred for USB are transferred as packets in 4 different transfer types. Interesting for us are only interrupt and control transfer. You basically have isochronous transfer and bulk transfer too, but we will just skip them. Interrupt transfer is used once a key is pressed and it is sent to the system. And they are used for a small amount of data, and retransmission is supported by USB. Once the packet is lost or anything happened, it is retransmitted 3 times. And then you have like the control transfer, which is used to set or get the device configuration. And the cool thing about it, we will see later, is it is acknowledged in both directions. Okay, for USB, we furthermore have different device classes, which is the reason you actually can plug in any USB stick or keyboard and it will just work out of the box. And relevant for us is the human interface device class. In that class, it is actually defined how the keyboard communicates with the computer. And we basically have the following communication. The keyboard can send 8-byte input reports to the client, to the computer. They are sent as interrupt transfers, polled by the host for sure, like I said, and it looks like that. You have 8 bytes, you have modifier keys, OEMUs, and 6 bytes for key code. The 6 key code bytes actually are also the reason why you only can press 6 keystrokes on a USB keyboard simultaneously, because the package just takes like 6 keys. And that's it. We have no make codes, no break codes. Once a key is pressed, it is in that package. Once it isn't pressed, the entry is just zeroed. The PC to the keyboard in return can send 1-byte output reports. They are sent as USB control transfers and are basically just used to set the LEDs of the keyboard. They don't have any other use. And the packet looks like this: 1 byte, 8-bit. You can see 1 bit for numlock, caps lock, and so on. You don't have any additional keyboard commands like we had for PS2. The transfer is handled via USB. That means retransmission and stuff isn't necessary here. And the typematic rate and stuff isn't configured on the keyboard microcontroller either, but all the logic is implemented on the client side in the operating system. So basically, I had some similar ideas like I had for PS2 when it comes to USB. I thought if you look in the device manager, that's cool. You actually can see how much current a device draws. So maybe we can detect that keyloggers. But problem is, the device manager doesn't show how much current is really drawn. It just shows the value the device sent during its configuration. In its control transfer, once it is configured, it says how much current it wants to consume, and that's the value displayed in Device Manager. You don't have any sensors or stuff on your motherboard either to measure how much current is drawn by USB. So forget it, you can't do it with current measurement for USB 2. It doesn't work with current hardware. So the next thing I stumbled across is for the Keylogger Keycarbon, there's actually a software used to read out the keystrokes. And the cool thing is, once there's a software to retrieve the keystrokes, maybe I can use the same technique the software does to get them and thus detect it. So what I did, I got a software-based USB protocol analyzer and analyzed what or how exactly the software communicates with the keylogger. And yeah, that's actually a dump from it, a small one. You can see the control transfers. The PC can send the 1 byte control transfers I use to communicate with the keyboard. That's also the reason all the LEDs blink up while you run the software on your keyboard. And yeah, you can see how it is used. If you look deeper into it and analyze the output reports used, you can determine there's a fixed header. Whoop. Here we are. There's a fixed header. Then we have the password of the hardware keylogger that is sent. And then we have like a footer. For the password that is sent in that communication, every password char is encoded within 4 control transfers, which actually means 4 bytes that are transferred. So what you can do, you have the header, you have the footer, and you just can create a lookup table for the password chars, and you can try to brute force the model via software, basically. And yeah, it works, but it just works for Keycarbon models since it's the only vendor I found that actually provides a software to read out the keystrokes. Yeah, sad. The next thing, it is more obvious. Yeah, can we do the questions at the end, please?
Just a small question.
Okay.
Do you get a negative feedback if the password is incorrect?
No. Yeah, that would be cool if it would respond if the password is wrong, but it just doesn't. Normally, the software sends its password, and if nothing happens, it just does the same stuff again and again and again because maybe data might be lost, but the keylogger doesn't respond at all, sadly. Yeah, it would be cool if it would be that way. Then we could detect it very easily. Yeah. The next thing, which is more obvious, are changes in USB properties and topology. That's like it looks for my notebook. We can see root hub. We have port 1, port 2, and on port 2, the keyboard is plugged in. Now, if we plug in a keylogger, it looks like that. Did you see it? The Keycarbon? What actually happens? On port 2, it just places a USB hub with 4 ports on that port and plugs in my keyboard to that port 1. So it just introduced a new hub. Yeah, okay. But that's no problem. Yeah? The vendor says, why is the device undetectable in practice by software? The device shows up in Windows Device Manager as a generic USB hub. This generic USB hub has no ID strings and is indistinguishable from the generic USB hub found in 90% of all USB hubs. I mean, at first, that's pretty cool that you say, we are undetectable. Okay, we introduce a hub, but we are still undetectable because it looks like all hubs. I mean, if you don't plug in a hub to your keyboard, you'll probably get suspicious at that time already. But anyway, the statement isn't correct either, because if you take a closer look at the device descriptor, you actually can find the vendor ID and the product ID. Vendor ID, Texas Instruments. Product ID, that one. And guess what? If you open the hardware and look at the chipset inside there, you will find the USB hub controller that's used is a Texas Instruments TUSB 2046B. And okay, so if a new hub comes up in your keyboard topology and it has that host controller, probably I would take a closer look at it. The next thing is the key ghost model. It changes device properties. Like if you only plug in your keyboard, I have a packet size of 8 bytes, which is like a low-speed USB device. However, if I plug in key ghost, my device properties suddenly change to a packet size of 64 bytes, which represents a full-speed device. Furthermore, the device status is changed. If only my keyboard is plugged in, it's bus-powered, which is correct because it is. If I plug in the key ghost, it suddenly says it's self-powered. Quite interesting for a keyboard, but okay. I will give you more details on this later on, why it actually looks like that. The next idea, similar again to PS2. You can see the similarities. It's time measurement. Since the hardware keyloggers are placed inline, you can see it here too. The keyboard starts a transfer, keyboard stops a transfer, and you have a dislocation at the keylogger. So you can, basically, the idea is the same like for PS2, to measure it, and the only problem is before we had various KBC commands we could use for USB. We don't have those commands. But the cool thing is, I said, the 1-byte output report the computer sends to the keyboard is sent as control transfer. And control transfers are acknowledged in both directions. So that means we can send data that is acknowledged, which basically is like a ping again, which we can use. And so we can apply the PS2 techniques to USB as well. And the implementation does basically look like that. Send an output report to keyboard, wait until it's acknowledged, do that various times like we did for PS2, and just measure the runtime of it, and we are fine. The cool thing about that is you don't even have to go to kernel land because timing differences are bigger, and you can do it from user land, e.g. using libUSB. These are my results for that. You can see the keyboard and the amount of milliseconds it takes to do so, and with the keyloggers in place. So you can see there's that slide. Amount of time it takes, just more time. So we can detect USB-based hardware keyloggers using time measurement too. Basically, we have to create a baseline. In that, we have to consider whether we plugged in hubs and stuff, because if we would introduce hubs in our topology later on, the timing would increase too, and we would have false positives. And then we can measure again at a certain moment and detect it. Another cool thing I came across is different keyboard behavior. For the key ghost, if I do the following, I do an interrupt read on USB. For 8 bytes, I get that data. Then I send an USB reset to that device. And of course, if I do an interrupt read again, all the stuff is 0. The device has been resetted. If the key ghost hardware keylogger is present, I do an interrupt read, I get the data. They're the data like we got here. Then I do an USB reset. I do an interrupt read again. I get the same data, which is quite strange because they should be zeroed right now. So what I did, I looked on the wire, and you have to know during an USB reset, both data lines, D plus and D minus, are pulled 0 for a certain amount of time. And you can see before the keylogger, they are pulled to 0, and after the keylogger, there's nothing. So basically, the device just doesn't pass the USB reset to the keyboard. The keyboard never receives the USB reset, and that's the reason it doesn't behave like I think it should behave. And if you take a close look at the hardware again, you can see that a USB single-chip host and device controller is used, which is ISP 1161 A1BD. And it basically acts as a device for the PC, and it acts as a host controller for the keyboard. Now you might imagine why the device configuration changed, like I told you on the slices before. The reason is just it acts as its own device, and it is a full-speed device, and it says it isn't bus-powered, but it is powered otherwise, and so that's the reason for the whole behavior. And the stuff with the USB reset I just showed you, you can measure to or detect to in software. Just use libUSB, do an interrupt read, send a USB reset, do an interrupt read again, and you can detect it. Furthermore, you can use time measurement for that bug too, because since the single chip host and device controller is used, and it is a full speed device and doesn't pass the USB reset to the keyboard, you can reset it, and the amount of time it takes until you can access it again is less than it is for the keyboard. So doing an USB reset and enumerating the device again is faster once the keylogger is present. So my conclusion about the whole stuff is for PS2, all models I got into my hands were placed inline somehow. You could use time measurement as a general technique to detect all the models. And the cool thing is, you can even defeat them by switching to scan code set 1. It worked for all the models I got into my hands. For USB, it's a little bit different. I would say most of the models you can detect by changes in the USB behavior, like we've seen additional hubs or changes to device configurations, non-passed USB resets, that kind of stuff. But you have also more individual bugs since those devices are more modern, have more logic, more functionality. So you can also start to look for individual bugs like we've seen with the software to read out keystrokes. But I'm currently on that topic and probably more research is to come. What you can say as a complete conclusion, all keyloggers I got into my hands could be detected. There were generic bugs, there were individual bugs. Once you combine them, and like for example I showed you for the Keyghost USB keylogger, you have like 3 techniques to detect it, and if you combine them, you can create like a pattern to ensure it really is present and it's not a false positive, and maybe you can even say which model is present. If you want to try out all the stuff, I always say, I will release the code soon, I didn't yet. I hope I will find time in the next weeks, maybe you have luck. And the project at Google Code is already registered, and yeah, I think maybe I'll upload it within the next weeks. So that's it. Thank you for your interest, and if you have any further questions, feel free to ask. I guess we have one right here.
You had the statistics about the timings for the response of keystrokes.
Yeah.
How stable are they across different keyboards in laptops? Let's say this is a Dell, this is HP. How stable are these numbers?
Yeah, that's a good question. The problem is, like I said, I implemented it for my computer and it worked for my system. It basically depends if you count number of clock cycles and stuff on the CPU too, on the keyboard controller you have on your main board, and on the microcontroller within the keyboard. So basically, the CPU you could eliminate by just, depending on the CPU speed, measuring the time. So you have the 2 factors, keyboard controller and microcontroller within that keyboard. For those 2, you always would have to define a certain timing for this combination. So basically, yeah, you have to take a measurement for your clean system and define a baseline. Once you use another keyboard or another motherboard with another KBC, it won't work. Yeah.
Do we have one last question? There's 1 minute left. No one.
No further
Excellent.
questions.
I'm sure Fabian will be around
we
anyways.
have one.
Okay.
So to continue on this, this means you really have to have fingerprints of different keyboards. So what you have done in this direction is only for your privately owned single keyboard so far.
Right. It's only for my keyboard. You would have to define like a database for each combination and stuff. And the problem is for PS2, you can't detect which keyboard is present. For USB, you have the vendor ID, device ID, but for PS2, you can't determine which keyboard is present. So you would have to define manually, that is my keyboard, in order to get the correct timing. Yeah, sadly, it's like that. It's just a proof of concept for my system. Yeah?
Would you wait for the microphone?
Sorry, would you see differences between different keyboards of the same make? Due to build quality or whatever?
No, I actually had various Cherry keyboards when playing around, and it worked with them as well. They had the same timing. Once you have the same brand and stuff, there were no problems. Yeah.
Okay, so as we're running out of time, I'm sure Fabian will be around for the rest of the afternoon.
Yeah, sure.
Thanks a ton again for the speech.
Thank you.